Okay. Good evening, everyone. Good morning, Rick, and good morning, everybody else who's joining from abroad. Welcome to this Incose India chapter webinar. This is our fourth webinar in the series this year, and I'm very much excited to welcome Professor Rick Hefner from Caltech, who'll be talking about resiliency in systems engineering today. Before we start with the topic, I'll just give a brief background and introduction to Incose India chapter and our accomplishments so far. So the Incose Central actually has over 18,000 members with 53 technical working groups and with 74 plus chapters across 35 countries and 3701 certified professionals with 120 CAB organizations. So Incose, as you all know, is celebrating 30 years of this year, and Incose India is actually celebrating 10 years this year. And it's a great pride to tell you that since 2015 to 2018, we have been consistently getting a Silver Circle Award. And in 2019, we were awarded with Gold Circle Award. And also this week itself, we got an award for most improved performance in 1 year. And so just to give you an idea of the Incose India background, we were chartered as an India South chapter in 2010. We have about 160 individual members and over 180 CAB associate members with us. And as you can see, the certified professionals with us, we have 61 SCPs with 2 ECEPs, 17 ACEPs, and 42 CCEPs. And currently we have 3 active local technical working groups, the architecture working group, model-based systems engineering, and PHM, which is the prognostics and health management. So without further ado, I would like to welcome again Professor Rick Hefner for today's topic of resiliency in systems engineering. And just a brief background, Professor Rick is the program director of California Institute of Technology. He specializes in systems development and maintenance, project management, Lean, Six Sigma, process improvement, technology transfer, and risk management. He has experience of over 40 years and working with multiple companies in aerospace, communication, electronics, and health science. And he's been credited with over 200 publications and presentations. He has earned his Ph.D. from University of California and in applied dynamic system control. With this, I'll hand it over to Rick. Over to you, and I'll stop sharing my screen.
Thank you, Budit. I appreciate the opportunity to talk to Incose India here. And we have a really interesting topic for today, the idea of resiliency in systems engineering. Resiliency is a topic that's been going on for a couple of decades, probably in the research community, but has picked up a lot of interest lately. It's currently kind of one of the hottest topics, along with model-based systems engineering. It's one of the hottest topics. What I hope to do today is just give you a little background on resiliency and tell you a little bit about the history of it and some of the design techniques. We'll start with kind of the definition of it. It's the ability to provide the required capabilities that we have for our system in the face of adversity. So adversity in this case being any condition that could degrade. We'll get more into some of the detail there. But as you can imagine, so many systems now that we design can fail in different ways. And there's lots of different design techniques that can help us address those failures, help make our systems more resistant to failure or more adaptable if a failure does occur. And so that's what we'll be getting into a little bit. I'll be happy to take some questions here at the end, and I'll leave some time at the end to address some questions. So again, our definition here, the ability to provide a required capability. So every system that we design and build is built to provide some capability. There's some performance, there may be functionality that the system provides. And if I think of adversity, right, I normally think of failure, okay, something that's going to cause a system to fail, or even something that causes the capability of my system to degrade. So think of a network, for example. Are there things that could cause the network to be able to handle less traffic than it normally would, or be able to only handle some types of traffic, maybe in a certain geographical area? And adversity in the resiliency literature, they typically talk about kind of three sources. So environmental sources, something that could happen in the environment. We think of things like floods or earthquakes. I think even the virus would probably count as an environmental source these days. So-called normal failure, or just sort of typical failures. So if I look at my network example here on the right-hand side, I could have some failure in one of the components, maybe one of the switching networks or one of the servers, or a failure in the database. That could cause a problem. And then failures could come from a variety of reasons. The component wears out, or there's something actually physically breaks, or electronically breaks, etc. Or the third category of adversity is human sources. So human sources could either be malicious. I've actually got somebody maybe trying to hack my system, and that's becoming an increasingly important area now. Or it could be accidental. Somebody accidentally does something. So we've got a network example here, just kind of showing that several years ago there was a problem with the with one of the phone networks in the U.S. and somebody was updating a database, and the database for the network had to do with what equipment was offline and online. And so if there was it's basically a large configuration file that identified whether a system was working or not, and so therefore they could switch and route around any not working equipment. And somebody was making a routine maintenance, and the configuration file was basically a bunch of ones and zeros, and the person making the maintenance fix put a period in the file where they should have put a comma. Very simple, very trivial mistake. The bigger mistake was, though, that they didn't test the file before they put it right into production. And so they had an existing system, they loaded the data file, and it immediately brought the entire network down. And the network was down for several hours. There were several millions of dollars lost in revenue from businesses for not being able to communicate. It basically took the whole eastern seaboard of the United States down as a network. Accidental, human source, yeah, but we start to think, could we make a system that's resilient? Could we make a system that would somehow not react to these kind of human errors or any of these other adversities? And so, of course, that's a very, very hot topic, lots of areas. There's really been an evolution in kind of thinking about this. And it kind of goes back to pre-60s, and when we built systems that are comparatively simple compared to what we build today. Back then, we kind of think of the era of technology. And if a system back in the 50s or 60s failed, we often simply focused on the hardware failure, okay? This is kind of a linear model thinking, right? We have a system, there's several things it has to do, there's several pieces of equipment it has to use, and if one of those pieces of equipment fails, the system's gonna fail. And so we focused most of our thinking about failure and resiliency on the failure of hardware. And so we looked at ways to make hardware more robust, less likely to fail. We looked at redundancy, those sort of issues. In the 70s and the 80s, we started to build a lot of systems where there were humans in the loop, okay? And humans add an extra complexity and extra new failure modes. And so we kind of got into this era of human errors, right? Where the problem was, like the network example I talked about, the problem was a human used the equipment in an improper fashion. They made a mistake in data entry. They used a piece of equipment in the wrong way. They configured something incorrectly. And so that was considered kind of a human error. And because a lot of times it wasn't just a bad human error, it was the fact that the human error also impinged somehow with the capability of the system that we didn't understand. So somebody leaned on the keyboard, and that combination of keys actually caused some failure because the system was in a mode where it couldn't accept that kind of a command. So this is what we call the epidemiological model, or thinking that the failures are due to a series of latent factors. If I put the right combination of inappropriate things together, that was how I caused failure. And so I started thinking about people studying resiliency said, you know, I just have to think about what are these inadvertent modes I could get the system into, and I looked more at how humans are interacting. And this led to kind of the 80s and 90s where we talked about technical interactions, right? So the idea is, could we build systems that the stakeholders or the users couldn't operate properly? So we started thinking about things like, or Chernobyl, right? So Chernobyl was a series of human errors that then got compounded with other latency factors, with mechanical design. And so what emerged out of that was a lot of industrial design thinking that said, I've got to mistake-proof my systems. I've got to make them in some way that, given the skills, given the culture, people, they would be resistant to failure. Challenger was another example, the space shuttle, where there were known problems in the design. There were no limitations of the design in terms of cold weather. And the issue was really cultural. The structure of the decision-making process at NASA didn't allow a proper consideration. There was a number of people that said we shouldn't launch Challenger, that we were outside the design envelope, but culturally, those people's opinions weren't heard, and so we went ahead. So we started thinking about the culture and the structure, sociological structure, and how did that help or hurt in terms of failures. And in the 2000s now, that's kind of given away to what we call the systemic model, or this idea of emergent variability, which says, you know, systems are complex. They have lots of emergent properties, both positive and negative. And a designer probably really can't anticipate all the different states and modes that a system might get into, all the possible interactions. And so if I'm going to safeguard against failure, I've really got to think about other mechanisms for resiliency. It's not a question of avoiding doing the wrong thing. It's a question of building systems that are inherently more resilient. And that's the kind of the current state of the practice that we're looking at today. So the other thing that's happened is we're doing a lot more systems to systems development now, and systems of systems just amplifies the resiliency challenges that we have. So when I think of a system of systems, I'm thinking of a system that's built in pieces at different times, so it's probably upgraded over time. One of the problems with a system of systems is the system just sort of grows and adapts over time. It wasn't any configuration that I have the system of any point in time was not designed top down. So I just put things together as my needs grew, as other systems got developed. And because I never really did a top-down design of the system, typically I don't even really investigate some of the emergent behaviors and some of the unintended consequences. And so we have systems where we add a new component, and that component causes the system to behave in some sort of unknown fashion. So in our example here, maybe we have a network and we add on, you know, another switch and a bunch of more computers as my business grows. And now maybe I've got, you know, too much requirements for the servers that I build or the router that I build, or now I've caused an internet because that switch is designed differently than a previous switch. Maybe now there's an incompatibility. The other problem with systems too is we're typically as strong as our weakest link. So I could add one component that was very prone to failure, and it drives the whole reliability of the system down. So in the example here, this little orange computer, I've added one computer that happens to be at a wireless access point. Well, it's easy to think of system designs where that one computer can bring the whole network down just because it fails in some sort of odd way. So I think the way we frame the problem now, the way we think about how to solve the problem is, identifying the pieces of the system. And so the first piece, we have to start with what's the capability of interest? What are we trying to safeguard against? So if you're working on a light rail system, right, you'd like the system to be safe. You'd like it to properly operate on the tracks. You'd like it to be comfortable for the passengers to ride in, etc. There might be several different capabilities. I might care a lot more about passenger safety, for example, than I care about passenger comfort, right? Comfort would be nice to have, safety would be required to have. And I've got to figure out how I'm going to measure the capability. Often these are quality attributes that are not measured directly, something like passenger comfort. How am I going to measure the comfort of the passengers? That might be. And then I've got to start with some target levels. And I might even have target levels by, target values by level. For example, maybe there's a nominal value I would expect the system, but in certain times, like maybe rush hour, I might have a degraded mode that's more acceptable. Also have to think about all the different modes of operations. There might be operational modes, there might be training modes, exercise modes, contingency modes, maintenance modes, other things. I've got to specify all of those. I've got to consider a set of adversities. So I can't just do this for general adversities. I have to think of specific things that could happen. Okay, what happens if there's something on the track for the light rail train? What happens if there's a passenger car in the intersection, right? So specific types of failures. And we do failure analysis and FMEA studies and fault trees and things like that to try to think through all the different adversities and what's the effect of that adversity on system capability, okay? It's also appropriate to go time frame. There might be things that cause a system to fail very briefly, but the system recovers quickly. Or there might be sort of persistent adversities like operating in wet environments. So maybe I'm doing a light rail in Seattle, Washington, in the US, and it's always raining. And so the adversity issues are always there, right? So I got to kind of frame the adversity. And then finally, I've got to think about what's the required resiliency that I want. What is the expectation? If there's an earthquake, do we expect the light rail system to remain safe, or is that really beyond the state of the art in terms of what we can do? What's the maximum allowable degradation we can get in performance? Or if the system had to shut down, how long is it acceptable to be shut down? I spent a lot of my career designing satellites, and satellites have all kinds of different problems that happen to them. And the question is, well, how long could a satellite be in a degraded mode? There was a difference between a mode where we couldn't do the mission or a mode where the satellite wasn't stable and the entire satellite could potentially be lost. So again, could have several levels of goals. I could have threshold goals and objective goals. I could even say, well, I want the system to be as resilient as practical, right? Maybe it would be prohibitively expensive to make things perfectly resilient. For example, the space shuttle has had 5 redundant computers, right? But many, that's an incredibly expensive system. Most of the systems we build in everyday application, we couldn't afford to put that kind of redundancy into our system. So it wouldn't be practical. And so money gets into an issue here as well. So looking a little bit more at diversity, let's talk about different kinds of disruptions. And the literature talks a little bit about kind of two types. What's called type A is a disruption in input. So a disruption in input typically means there's some sort of unknown or unexpected phenomenon. At least when the designer designed the system, they didn't envision something happen. So you look at the New York Twin Towers attack, there wasn't, those buildings weren't really designed to have a passenger plane fly into them. So I don't think the designer probably thought about that when they thought about the design of the system. Type A disruptions can also be, some really unexpected or unlikely situation like a major change in the environment. So Katrina, right, the hurricane that hit the Katrina hurricane and the flood in the U.S. Again, overstressed dams and levees and things like that probably were not designed to experience that drastic a change in the environment. The other type of disruption or adversity we call type B, which is just some degradation in the function or capability of systems. So typically these are smaller component failures in the system. Could be a software error, could be a human error somehow, where the human's involved in the system. Could be a component failure, like in the case of Challenger. Could be some sort of interesting interaction between components that we didn't expect, some emergent property. So I have a little video and I'll kind of show it. And this little video is, I want to set up, it's on the Tacoma Narrows Bridge. And that was a bridge designed many, many decades ago. At the time, it was the third biggest bridge of its type in the world. And the designers designed that bridge using everything they knew at the time. But there was some phenomenology about resonance frequencies of structures that they didn't really understand the idea of dampening in bridge construction before, and the results were sort of catastrophic. So let me play a short video, just kind of show you an example of a type A disruption.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
So pretty dramatic failure there. And this was a type A disruption in that the designers didn't really understand the phenomenology of natural structural resonance. And so what happened was when the wind got to 35 miles per hour in that pass, the bridge started to sway. And because bridge construction at the time didn't think about dampening effects, that swaying just continued to amplify, and as a result, you can see it sort of tore up the bridge. I always feel bad for the dog. They actually sent the dog across the bridge because they thought the pattern of the dog's walk would somehow change the frequency of the bridge, and it was, the dog is way too small to actually have that kind of effect. Same thing, they thought somehow inherently putting the car on the bridge would have a dampening effect, which it did, but of course it wasn't nearly big enough. So when we talk about this failure state, if I look at the upper right-hand corner of this graph, we kind of think of frame the discussion by saying there's a certain amount of functionality we've got, and we're kind of going along in the nominal mode, and then something happens. There's an event, a specific problem occurs, and it may be gradual over time, or it may be maybe sudden breakage of something, right? And at that point, the capability goes, way down, or maybe even to zero. The system totally fails, and then some period of time at which I recovered to some sort of capability at the end. And so we think about different states we can get in that have to do with how long the failure event takes place over, how much the recovered capability is close to the original, the functionality of my system, et cetera, what the timeframes are. So this is just a little failure state diagram that sort of talks about different states the system might go through as we think through a failure, from sort of nominal performance to maybe a heightened awareness. The system or the operators have a sense that something's kind of going wrong, to maybe states where the system might be damaged but still provide some functionality, right? Or the functionality might be partially disrupted or non-functionality disrupted, which means I'm doing all the things I'm supposed to do, but maybe I'm not doing them to the level that I need them to do. The accuracy goes down, maybe, or precision goes down. I could even get into states where I've agreed to modify the state, or I've got a new modified system, or to states where I actually have to decommission or basically take the system out of operation, or even in some cases the system might destroy itself as well. So a resiliency engineer has to kind of think through all these different failure states and what ones can get into and which ones are acceptable from the point of view of our stakeholders. Several different ways we might achieve resiliency in a system, and we're going to kind of transition now into specific design techniques that I might consider. So I can try to avoid the failure. You do something to keep the failure from either happening or keep the failure from affecting the system. So you can think of something like maybe electronic shielding or physical shielding or hardening, where I'm just trying to, I can't control the adversity, but I can make sure the adversity doesn't have as big effect on my system. Withstanding is just to kind of sit there and take it. So accept the impact of the adversity, but continue operating despite it, right? And maybe sometimes that's at a reduced level. So something like building redundancy into a system, I might see a failure that causes part of my system to fail, but I continue operating, maybe I'm not operating at as much of a capacity, but I still I've withstood the adversity. Recovering says I'm going to accept the impact, but then I'm going to reconfigure my system in some way so I recover to some operating capability, and it may or may not be the same functionality that I have. So a system that is serviceable, right? An operator could be part of this, and so the operator recognizes something's broke, and they replace the broken part. So they basically recover the system, and often they can recover it to full capability. And then more complicated means like evolving and adapting. We could have systems that actually sense the adversity and adjust over time. So there's a number of systems that have some type of failure detection mechanism, and they can actually reconfigure themselves kind of on the fly to adjust and provide resiliency from that perspective. By the way, there's a really good article in the CBOC wiki. So I put on system resilience, and it goes through a lot of the things I'll be talking about today. And so I'd really recommend that to you. And then I've tried to call out some other references here in the material, but that particular article is a good starting point because it points to about 20 good solid articles in the field, and it's a very, very good summary. There's also a system resilience or resilient systems working group in INCOSE, and anybody can join that working group and they wrote this article and they write other things from time to time too, and work on that. And that's another good way to kind of tie into the community work in resiliency. So 4 attributes that we might look at in any system that contribute to resiliency. So robustness, adaptability, tolerance, and integrity. These are discussed in a lot more details in a work by Scott Jackson and Tim Ferriss, who are kind of 2 of the key researchers in this area. And so I'll point you towards that, but I'm going to go into each of these in a little bit detail and talk about what some of the design features are that contribute to some of these attributes. So robustness, so that's the ability of the system to withstand a threat in the normal operating state. So the system is robust if things can fail, and it just kind of stands up to those threats. There are kind of 3 main design techniques that we use to try to make a system more robust. One is these are really not kind of cookbook designs. They're really more like considerations that I might think about in terms of how I design the system. So one is absorption. Could I design a system in some way that it just basically absorbs the issue and doesn't have a fundamental breakdown? And I can do that through a variety of ways. 2 specific approaches are things like physical redundancy, where I've got maybe a duplicate of a component that is likely to fail or be affected by a failure, and either component can provide some critical task. Or I've got some sort of functional redundancy, so my system has the capability to perform a task in several different ways, and so if one way is disrupted, I have something else. And I think a simple example of a robust system is something like a laptop computer, right? The laptop computer is designed to be very robust against a number of different adversities. So for example, laptop computers can take a little variation in heat or humidity and continue working. The parts have enough tolerances, et cetera, that 10 degrees of temperature probably isn't going to cause the system to fail in some way. They're also physically redundant. I think most laptop computers now, for example, have several USB ports. So if one of your USB ports went bad, you have other USB ports that would do the same thing, and so there's some physical redundancy there. And even things like functional redundancy, if one of the functions, for example, would be to accept a new file, there's several ways I could get a file into a computer. I could use a CD drive on the computer. I could use a USB port on the computer. I could access a network and download it their way. So laptops are inherently designed to be very, very robust to take advantage of this attribute. Adaptability is a kind of a second attribute I'd like to have in a resilient system, and that's the ability of a system to restructure itself in the face of a threat. And so restructuring is a particular design system that can reconfigure themselves. When I put a human in the loop of a system, often the human is there to be able to adapt the system. So if something's not working quite correctly, the human is there. So I've got an example here of a light rail train called the Metrolink, and there's a human driver up there. And so if there's something on the track, or the engine's not working quite properly, or something else that's unexpected, the driver of the light rail is there to take some actions. Right? It makes the overall system, counting the human as our total system of interest, it makes that system more adaptable. Another design principle is this idea of complexity avoidance. I want to make the system as simple as possible, so no more complex than required. When I add unnecessary complexity to the system, I create additional infrastructure that typically causes my system to be less adaptable. Simple systems are usually the most adaptable. And so designers try to keep systems simple as they can, not make them incredibly complex. So if I can use one part instead of 10 parts, I would always try to do that. And then a more complicated design technique is the idea of something called drift correction. Drift correction says, as I start to drift away from a nominal condition, the system itself would sense that and try to bring the system back into nominal. So think of a regulation on the light rail that recognizes that the train is going too fast for a given condition and automatically applies brakes. And so I have a little bit, I have a video here that's going to talk a little bit more about adaptability in a more complex way, and it's probably kind of a state-of-the-art resiliency design here. So let me play the video for you.
Southern California's MetroLink is among the busiest commuter rail services in the United States, carrying over 1 million passengers a month. To improve the safety of this network, MetroLink will introduce Positive Train Control System, a state-of-the-art collision avoidance technology. The Positive Train Control System uses computers and servers located in trains, global positioning systems, wayside signals, and central offices to establish continuous real-time communication over a digital network. All trains traveling on MetroLink's rail network, passenger or freight, are linked. Through the use of highly accurate next-generation GPS, the PTC system provides train crews continuously updated visual and audible data on the status of approaching signals, the position of approaching switches, speed limits at approaching curves and other reduced speed locations, speed restrictions at approaching crossings, and speed restrictions associated with areas where work is being performed next to or on the tracks. The train's onboard computer constantly calculates and displays the safe braking distance based on the train's speed, length, weight, and the grade and curvature of track. The engineer is provided ample warning time to bring the train to a safe stop. In the event that the engineer does not respond to the display and audible warning, the onboard computer will apply the brakes and bring the train to a safe stop.
So you can see that's a system that has a combination of adaptability techniques. For example, being able to display something to the human in the loop and the human takes an action, but then also having a fail-safe system. If the human did not take an action and the system still realizes that the adversity was escalating, then the system itself would cause the train to come to a stop. You see similar kinds of complexity in this in terms of like autonomous cars, right, who can sense their environment and take actions as a result of that, even though the human in the loop can override at times as well. Third type of ability, attribute that we want to consider in terms of resiliency is something called tolerance. Tolerance says, I'm tolerant to the adversity. I can allow the system to degrade in a graceful fashion following some encounter. What I'm avoiding in tolerance is I'm avoiding sort of catastrophic failure. So we sometimes call it graceful degradation. You know, the performance as a failure starts to emerge, the performance fades off in kind of a gentle way as opposed to sort of a bang breakage. Lots of different design techniques make my system more tolerant of failure. So things like modularity. Breaking up the functionality through different nodes so that if one node is damaged, the others can continue to function, a failure just doesn't ripple through the system, for example. Loose coupling is another idea. Make the systems loosely coupled so elements operate independently of each other, and that keeps unexpected interactions, the failure of one thing causing failures in other areas, etc. We also talk about the concept of a neutral state. A tolerant system always has a neutral state, which is the state that I want to put the system back into if there's a disruption. Our computers, for example, have certain failures. And in the case of a failure, it's going to shut down the application and put the system back in a neutral state where I can't continue to take damage from the adversity. Repairability is a capability. If I build into the system design the ability to bring a system back from certain types of failures. And repairability always has some parameters associated with it, like it may take me a specified time to bring the system back into capability. There may be certain environments where the system could be repairable, maybe other environments where the system couldn't be repairable. And repairable could either be the system does that automatically, or it could be that a human is part of that repair. And a more broad and more in-depth idea is this idea of something called defense in depth, which defense in depth is a way of saying I'm not going to have a single point failure. I'm going to have more than one way to address a vulnerability in the system. So maybe I have a ability to reconfigure the system, but I also have some redundancy, and so I have multiple effects, and especially when I'm in high failure environments where there are a lot of continual adversities. I often need several mechanisms to be able to repair a system, or at least to keep a system operational until a human can come in and start to do more drastic repairs. Integrity, another area. This is the idea of wholeness or cohesion in the system. So it axifies in a unified way. And I don't mean that in opposed to modularity, but I mean the system itself, all aspects of the system recognize this threat. And so a couple of design techniques there. One is something called internode interaction, where if every node in the system can communicate with every other node of the system, then we can keep communications flowing even if there happens to be a failure. The other thing is if I want to try to reduce hidden infrastructures. So potentially harmful interactions, the biggest problem with systems sometimes is they're so complex that we have all these interactions that we don't really recognize, or we think as a designer, oh, we're never going to get the system into that mode. Well, in our complex systems, things always happen, you know, a lot of times, especially if there's humans in the loop, people operate the system in some sort of inappropriate fashion. They trigger some sort of hidden infrastructure that we didn't think about. In the software world, for example, we have a rule where we don't leave code in a legacy system that we're not going to execute. And you say, well, why take the code out? We're never going to execute it. Yeah, but maybe something weird will trigger in a way, and somehow we'll end up executing this code that's unproven, and that'll cause a failure. So in general, if I don't need it, I'm going to take it out of the system so that it couldn't possibly get triggered, even if it gets triggered in some way that I didn't really intend, didn't really anticipate. Let's see. There are lots of other perspectives. I'm giving you kind of some summary here, but lots and lots of researchers. The work of Britis and McKelvey, I think, is very useful. They've written several good ideas, and they take these engineering techniques, these kind of 4 attributes, and they expand them out into a bunch of very specific materials. So we don't have time to cover all these different methods today, but I think most of them are several are useful. So kind of a broader set of these techniques, and they talk about the objectives of each technique, there being a list of things that we think about as characteristics of a resilient system, right? The ability to adapt or to anticipate or disaggregate are all steps in a resilient response, if you will. So would point you towards the work there of MITRE and their discussions. They certainly worked on a lot of good advanced systems. Scott Jackson, we talked about earlier, he's written a lot of good works on the subject. And one of the best textbooks here is something called Architecting Resilient Systems. And in that text, Scott talks about different failures over time, and he looks at kind of what was the rationale. And often we recognize the capabilities of resilient systems by looking at a failure and then recognizing in hindsight what was missing from the design. Okay, we didn't think about that section of that interaction. That was an interaction we probably could have eliminated if we had thought about it. Or we didn't think about that cultural impact in terms of the way the humans interacted with the system. And so now in hindsight, that makes sense. And so he has a lot of ideas about system resilience and what the enablers are for it, and how I break that down into things like culture and managerial technical capabilities. And as you can see, it's quite an extensive perspective on system resiliency. You know, there are so many different options for system resilience that we might think about. And so these taxonomies and hierarchical structures are just designed to get you thinking about more innovative ways to build resiliency into your own systems. So in summary, let me just say that I think systems engineers have to consider resiliency now in designing their systems. We have failures. They're often very catastrophic. At the very least, they cause disruption in the capabilities of the systems that we design. And there are multiple design principles that exist out there that can be used. Most of those are uncovered by looking at failures and recognizing the missing design principle, or thinking about systems that are inherently more resilient and what ideas. The real skill is selecting and applying the appropriate ones for your given application in your given system. And that's something that we're all learning to develop over time. So that's a quick summary on resilience, and I'd be happy to take a few questions here if anybody has them.
Thank you, Rick. We do have a couple of questions on the chat, so I'll just start with those. So the first question is from Prashant Mohan. He asks, do we have any ISO standard that provides recommendation on processes or activities related to systems resiliency?
Prashant, I'm not aware of any ISO standards like that. I think we're still emerging that. There's certainly ISO standards on failure and classifying failures, its severity, its frequency, but we probably, and there certainly are standards that address particular design features, but not one on resiliency that I'm aware of as a whole.
Okay. The second question is from Nikhil Joshi. He asks, how can we report a resiliency level for different capabilities of our system, apart from listing its features of robustness, adaptability, tolerance, integrity? More importantly, how can we compare resilience of alternate system designs?
Yeah, great question. So if you look at the system resilience article in the CBOC wiki that I cited earlier, there's a whole discussion on how do I measure resiliency of a system and how do I specify resilience. I think specifying is even a more difficult. If I had to make a resiliency requirement, how do I do it? And it follows this kind of thinking that this framework that we use for a lot of quality attributes, which is you have to define a scenario and then define what's acceptable performance in that scenario. So in this case, the scenario would be some type of a failure and then the response of it. So lots of detail on it. You're typically going to look at it with kind of failure thinking. You know, what's the class of failure? What's the expected response? What's the time frame of the response? And so I refer you to that paper. A lot of good detail there, kind of more than I can cover in a couple minutes.
Okay, we have a couple of questions that are related onto correlation. So we have a question: can one correlate system resilience with risk management? risk management plan also can give you rise to thought of system resilience. And then the second question was, what is the difference between DFMEA, reliability and resilience, and how it correlates? So,
yeah, there's a very strong correlation between risk management. When I think of resilience, I'm thinking of risks in the operational environment. So sometimes if I'm doing risk management on a project, I'm thinking of risks in the development or design process. So we have to make that distinction, first of all. Things like design FMEAs and other kinds of FMEAs are very strongly related to risk. That's typically how I establish what the adversities are. So I start to identify. So those FMEAs typically talk about the failure and what the impact of a particular failure would be. But they don't get typically into design. So design is the issue that we really want to worry about in resiliency. Now that I know a failure is, what can I do to mitigate that failure? So in that sense, there's a lot of commonality. The extra dimension that resiliency throws in is the idea of not failing, but actually degrading performance. So is there something that causes my system to work slower, less accurately, less reliably, maybe decreases the overall life of the system, but doesn't actually necessarily cause a failure of something. So that expands our FMEA thinking a little bit to degradation as well.
So the next question is from Swami. He asks, emergent variability seems to imply unanticipated adversity, but resilience design and analysis seems to focus on unidentified adversity. How are the two reconciled? Should some adversity be identified in terms of effects rather than root causes?
Yeah, you got to do both. So think about risk management. I worry about the known unknowns and the unknown unknowns. Known unknowns are things that I know could happen. I can envision them happening, but I'm not sure it's going to happen to my particular system. Unknowns are things I can't even anticipate. So resiliency, and I think you characterized it well. I have to look at both sources in resiliency. There will be things that I know could go wrong, or harshness in the environment, for example, that I'm definitely going to have to worry about. There can also be things that ideally my resilient systems would deal with that I don't know. So some sort of generalized resiliency or extra capability.
The next question is from Sandeep. Which are resources would you recommend to learn fault protection, which would impact systems resilience?
Yeah, I'll point you towards the CBOC Wiki article again. There's several. It's about 15 different articles that are cited there, and a couple of them specifically deal with fault protection. Scott Jackson also has a lot of good discussion of fault protection mechanisms, and so both of those are pretty good.
Okay. The next question is from Sandeep Oberoi. He says, I am the chair of ISO IEC SC7. Can I make an observation?
Yeah, absolutely. If you're aware of an ISO standard, I would love to hear about it.
Okay.
Yeah, so hello, Professor Hefner. And ISO IEC SC7 is the Software and Systems Engineering Subcommittee. And we have identified resilience as one of our strategic priorities. And INCOSE has been a very, very integral and valuable contributor here. We have set up a study group. We are intending to look at specific aspects that we should standardize, because a lot of standards talk about resilience, but there isn't any guidance as to what that means and how to achieve it. And I wanted to know if we were able to get in touch with you and possibly co-opt you and other volunteers from INCOSE to participate in that study and come out with standards track for the specific things that we can do relatively quickly.
Yeah, excellent. I would love to be involved in that. Thank you very much for the information. Yeah, I would be happy to participate, and it would help you make some connections with the resilient systems group at INCOSE as well, which I think has a lot of the authors that we've been talking about. So sure, absolutely. Thank you.
Thank you. The next question is, for tool development, how can we introduce resiliency in systems engineering?
So are we talking about resiliency in tools? Or are we talking about tools for building in resiliency?
I would request the person who asked the question to elaborate on this, please.
Hello. Hello, Mr. Hefner. I'm the person who asked the question about the tool development. Actually, I am doing my master thesis in John Deere in system engineering department, and I'm developing a tool which is integrated with the trade space analysis, like to reduce the human intervention of decision making process in system engineering. And one of the key factor which I believe that if I introduce the resilient and the resiliency factor in my tool development, it would be very much effective, and it would make it very prominent to have the tool in regard with the all the current state analysis and everything.
Excellent. That sounds like a very, very valuable effort. So I applaud you for the effort. Yeah, I think we need those kind of tools. We're starting now to look at model-based systems engineering tools that can model systems and therefore can consider failure modes. So a lot of times it's connecting an ops concept or a ConOps or some scenario in the system with potential failures and the way the components interact. Very difficult problem. So I applaud the fact that you're working your master's in this area, and I'd love to connect offline here and hear more about your details.
Okay.
So please reach out to me and let's talk more.
Okay. So should I message you in personal after this meeting?
Yeah, that would be fine.
Okay. Sure.
Yep. And if anybody is looking to connect with Rick or has any more questions, you can also drop an email to us, and I'll be happy to connect you with Rick.
Right.
Okay. Thank you.
And think that you folks are recording this, so that's there. And my contact information is here on the front slide, right. Or you can reach out to me through LinkedIn, and I'll be happy to address any kind of questions. So we have some more questions, maybe, Mudit?
Yes, we do. We have the next question. How the resilient systems graded and integrated into safety critical design assurance levels?
Yeah, obviously that's the general sense, right? We want to take our design concepts and then go back and think what's the resulting failure modes and safety modes of the system. Many times when we put in a design mechanism specifically to address a failure, we often create a different failure in the system. So I remember working on a system many years ago, and we were very concerned about a certain class of failure, and so we built a little failure detection algorithm to sense the failure and to try to reconfigure the system. And in operations, we never saw the failure, but the failure detection algorithm actually failed. And so we actually disabled the system inadvertently because the failure detection system was too sensitive and thought the system was failing when the system was actually working properly. So yeah, we've got to configure those kind of systems, and this has to be part of a whole assurance argument for the system. And you see that as a big topic right now, especially relative to cybersecurity issues, right? There's a whole rainbow series of manuals and books and frameworks for thinking about the failures of networks and the failures of applications, the failures of hardware systems that might be caused by cyber attack. Caltech actually just started a whole new cyber boot camp where we're trying to build a lot of these tools and techniques into protections. But the problem with that is as fast as you can think of protections, people think of new attacks. So It's constantly, we're constantly playing a catch-up game there. But yeah, you're right. It has very much to do with assurance of the system, especially mission critical systems, especially systems where human life is at risk.
We do have a couple of more questions, Rick. So just the second last one is how RAMs differ concept with resilience, RAMS?
Yes. Yeah, again, like FMEA, strongly related there. And when we're thinking about the reliability or availability or maintainability of the system, certainly degraded performance and resiliency becomes a major considerant in the RAMS calculation. So yeah, again, it's another very strongly related topic.
And then there's a last question, I think, on sort of scale and a metric. Is there any modeling system which can be employed to state on a scale of say 1 to 10 how resilient a system is, and the level of resilient system which is acceptable for a given mission the system is required to accomplish?
Yeah, there are some simple algorithms in narrow fields. So for example, for a network, there are measures of the resiliency of the network to normal disruptions. The trouble with those frameworks is they work very well in a very, very narrow environment. There's often other adversities that aren't addressed by those sort of frameworks. So I'm not aware of anything that's comprehensive that really looks at all that. I think some people are researching in that area, but I don't think we're quite there yet.
Okay. Thank you very much, Rick. I think that's the end of the hour and also end of the questions that we have on the chat. I once again thank you very much for joining us at your morning time. And thanks everyone on the call for joining us for the webinar.
Thank you. This was a nice session.
Thank you, Rick. Thank you. Thank you.
Thank you. Bye.
Thank you. Yep.
Thank you, Rick.
Thank you.
Yeah. Thanks.